turn on the projector. What you think? Is it Daniel?
Yes, sir.
Okay. I think he must have PE or something because he quite often comes in with his change.
He told me he's taking 2 PE classes this.
What's that?
Two PE class midterms.
Oh, okay. Okay. All right. Here's one of the problems. They keep asking me to make these announcements, but then there's usually so few people in here at the beginning of class it hardly makes it seem. But they're still looking for math team people. So I'm recording, so hopefully someone else will hear that too. Contact Miss Nyla Gerasi at on the Birmingham West Campus. I think they're meeting Friday afternoons, not this Friday, but most Friday afternoons, sometime around, I don't know. Do you remember what time? 11, okay, maybe Friday mornings 11. Sometime check with her on Fridays and you'll probably get in touch. This Friday we're going to professional meetings in Tuscaloosa, so we won't be, she nor I will be on campus this Friday, which is day after tomorrow. Wow, this week has been sort of strange. All right, I think, yes.
Today I'm going to have to leave about 2 minutes.
So minus 15 on your final grade. Okay. All right. Thanks for telling me. But it'll hopefully be recorded. I'm recording now. So if everything works, it'll still be there. All right. We're in Chapter 8, which is Integration Techniques and Improper Integrals. We're going to do integration techniques. The technique we're dealing with now is partial fractions. And we looked at several of the possibilities. The easiest of these are the linear factors. So that's where we're starting today. So any other questions before we get started? Okay. So jump right into one. Write the partial fraction decomposition for this. Not doing an integration yet, just a partial fraction decomposition. What would you do first? Get my pen set up. That's what we would do first. Okay, now what? Factor that denominator. And we are hoping it's factorable. Is it?
Yes.
What would it be?
X minus 3, X minus 2.
Perfect. I think we did this one before, didn't we? In fact,
it was the one they did on the,
what's that?
On the last page. It was the one they went through on the
Right.
last page.
And so well, I think I did more than I should have. And I believe I came up with it, didn't I? The total answer.
Yes, sir. Because this is the same one that they
Wait. Yeah.
And showed
This
how
is
to
the
do
very
it.
same one they did here. So we already know the answer to this. But no. They just said, lo and behold, here's what it is. I showed you how to get it.
Yes, sir.
That's all this example is doing, is showing you how to get it. So do we need to go through that again?
No, sir. It's
Okay.
just showing you how to get to the.
All right.
It doesn't give you an answer.
Huh?
It doesn't even give you an answer. It just shows you how to break them down.
Uh-huh. Okay. And, yeah. There are a couple of interesting things here. There's for further information, down here to learn a different method for finding partial fraction called the Heaviside method. See the article Calculus to Algebra Connections, Partial Fraction Decomposition by Weiner and Watkins in the AMATIC Review. We're going to Allomatic meeting this Friday. Okay. Now, they also make this little comment at the bottom. Be sure you see the method of partial fractions is practical only for integrals of rational functions whose denominators factor nicely. For instance, when the denominator in example 1 is changed to x squared minus 5x plus 5, you notice that it doesn't factor too nicely because you have radicals in it. You have to use the quadratic formula to come up with a radical. It would be too cumbersome to use with partial fractions. In such cases, you should use completing the square or a computer algebra system to perform the integration. when you do, then it shows you what your answer turns out being. Now, do you know what it means completing the square?
I remember hearing that in algebra.
Yeah.
I'm sort of confused on how it would work.
Yeah. It's just for a refresher here, and again, we won't do the integral because it is pretty complex, but here was the 1 over x squared. This is the argument of it, and you can extend this and do it minus 5x plus 5. So if you're trying to complete the square of the denominator, let's just pull it out of the denominator. We'll go and put it back in. X squared minus 5x blank plus 5. Now what do we put in the blank? Well, we take half of this coefficient here. Half of minus 5 is minus 5/2. Square that. That would be plus 25/4, right? But we just added 25/4 here. We changed the problem. Unless we subtract 25/4 here. Okay, now that doesn't seem like it seems like a fair thing to do, right? All right, now this is a perfect square. X minus exactly what this is, 5/2 squared. And this will be, if you write this as fourths, that would be 20/4 minus 25/4 would be minus 5/4, right? Okay. Now, huh? Okay. Here's where it came from. As soon as you took 1/2 of this, that gave you 5/2, right? And then you squared this and got 25/4. Then you subtracted 25/4. But this made this the perfect square of that. And then you had this. Well, if you were integrating this then, it's still a pretty big pain in the neck to do. This would be a form, you look at a table and find the form of u squared u plus a squared minus b or something like that, and you find a way to get to your solution that way. So it's not you don't lose all your difficulties. There's still some effort to be made. But fortunately, we're not going to have many like that, if any. Okay? And we've already worked the other one through, so let's move on to example 2. Well, wait. Let's see. I worked it through. Let's erase all this. We'll just do a quick talk through of what we did. Okay? You factor the denominator, and then you got a over x minus 3 plus b over x minus 2, just like you were suggesting. A and b are to be determined. Multiply both sides of the equation by the factored form, x plus 2 times x minus 3 times x minus 2. This one goes away, leaving you a 1. The x minus 3's go away here, leaving you a times x minus 2. And the x minus 2's go away here, leaving you b times x minus 3. Okay? Now, that's your basic equation. Now, to solve this should be true for any x. So, why not choose convenient x's, like x equal 2? And that would give you 1 is equal to, this goes to 0, minus b, so b is equal to minus 1. So then you'll go back in and put a minus 1 over that one. And then you put x equal 3, another convenient form, and that makes this go to 0, and that would give you a is equal to 1. So you put 1 there. So you have 1 over x minus 3 minus 1 over x minus 2. And that's exactly giving you a is equal to 1, b is equal to minus 1, and then this will be your decomposed fraction, 1 over x minus 3 minus 1 over x minus 2. Okay, just like we did last time. Okay, is that all they do? It is, but we can go back and do example 2. Makes a rhyme every time. All right. The much more difficult problem, and it's not that difficult, and of course they don't do that. The real simple one, they don't even do an integration of it. That was example 2. So example 1. This one, a much hairier looking problem. Let's see what we've got here. We've got the integral of 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x dx. Now, a little time out before we even begin this. What if this had been a cube up here? Or you divide first, absolutely. But since this degree is less than that degree, we move straight to our partial fractions. So good catch there. That's what you do. Now, partial fractions, what's your first step with that? Once you make sure the degree of the denominator is greater than the degree of the numerator, then use partial fractions. What's your first move?
You try and factor in one.
Yes, and how would you do that? First factor you always look for.
The highest degree.
Huh?
The one's got the highest degree.
Okay, here.
The one's got the highest exponent.
Okay, not quite. Actually, I go with the lowest. See if there are any common factors.
Oh,
Are there?
yes.
X. And what do you have left?
X cubed.
You factor that out an x.
X squared.
X squared plus
2x
2x
plus 1.
plus 1. Okay. Now you see if you can.
Oh, no.
What's that? Yes, this one you can definitely factor as
X plus 1 x plus 1.
times x plus 1. So that's a repeated factor, and it's repeated twice. Okay? So here's what we do. Okay? We write down, now we're not even doing the integral yet, we're just writing down, simplifying this. Write down your numerator, 5x squared plus 20x plus 6 over this factored form, x times, I'm going to write this x plus 1 squared. Now, there's two reasons I'm doing this. First is I'm a little lazy. I just don't want to write it twice. The second reason is to focus in that it is a repeated factor. Okay? Now, where do you go from there?
Would you go back to my
Right.
sketch?
Okay.
Linear factors.
First, we're basically going to break that into, and each of these are linear factors. So what would you have?
So you would have a over x plus 1.
Just start with x. A over x plus b over
B over x plus 1.
to the first power plus
plus c over x plus 1 squared.
To the second power. Perfect. Okay? That's what we do when we have repeated linear factors down there. We put constants over that factor, the first power, second power, as many as high as it goes until you reach your n. Here was 2, so we only went to 2. Now what do we do?
Now, you would
What's messy about that? The answer is denominators are messy about that. Speaking about messy about, no, okay. Here is Brian. I was telling Clark, I keep forgetting to make this announcement, especially at the beginning of class because so few people are in here. Miss Rossi, you know her, she's always looking for math team members, and y'all would be prime math team members. I think they meet on sometime on Friday, late morning, early afternoon, but not this Friday because she's got, and I've got 2 professional meetings in Tuscaloosa and Shelton State this Friday, so she won't be there meeting with her team this time. Okay, we're doing an integral that has binomial in the numerator, binomial in the denominator. First thing you check to make sure the degree of the denominator is greater than the degree of the numerator. It is. If it wasn't, if those are equal degrees or the numerator was a greater degree, divide first. Then come back and do whatever you need to do. But this one, degree is greater here. So you factor that denominator. Here's how it factors. This is a repeated factor here. So we rewrite this fractional form as the numerator, don't mess with it, over the, we really do need to mess with that. Not in this case, I don't think, but we always want to make sure we have no common factors between the two. So we really need to check and make sure that numerator, will it factor or not? We should have been doing this before. Completely forgot that. If it would factor, what would be the possible factorization? First one? Only way to factor 5x squared. 5x times x. Okay, got it. Now, if this is going to have a common factor, then this would have to be a plus 1 there, wouldn't it? For that to have a common factor. That would make this a plus 6 here, right? Because in your last factor, it must multiply to be plus, and this has to be plus. Okay. Now, does that work? 5x times x, 5x squared. 5x plus times 1 is 5x plus 6x, 11x, not 28. No. This may be factorable, but certainly you're not going to be able to get rid of x plus 1. So that's taken care of. We don't need, I kind of looked at it and thought to myself that, but I should have said, this is a step you need to do. Make sure it doesn't factor and has a common factor. So let's get back to where we were here. Once we set up this that we started with is equal to some partial fraction breakdown that a constant over the first factor plus a constant over the second factor plus another constant over the product of those two factors, x plus 1 squared. Once we write that step down, what's our next step?
Get a common denominator.
And what is it?
X times x.
Yeah, it's that thing right here. So we multiply this one by x times x plus 1 squared. We multiply this by x times x plus 1 squared. We multiply this one by x times x plus 1 squared. And we multiply this one by x times x plus 1 squared. Okay, I ran out of room. Okay, on the first one here, the x's go out. Okay. Oh, and over here, everything in the denominator goes out. In fact, all your denominators are going to disappear, which is a very good thing. Because even though we love our fractions, we'll get by with them without them if we can. So on the left-hand side, you have 5x squared plus 20x plus 6 is equal to, now, a times x plus 1, let's just write it down like that for now. A times x plus 1 squared plus b, and here one of those goes out, so it's b times x plus 1, right? You got one left. Here both of those go out, and you have plus cx. And that's all you have left there, with no denominators in sight, which is a very good thing. All right. Now what do we do next?
Convenient.
Yes, pick
X's.
a couple of convenient x's. What's one very convenient x?
-1.
X equal -1 will certainly be a good one. So you plug in x equal -1 to both sides of this. What does this give you here?
25.
No, 5. It's -1 squared, which is 1 times 5. Okay. Next, minus 20 plus 6 equals second, this one goes to 0, that one goes to 0, and this goes to -c. If x is -1, that'd be -c. So what do these add up to? -9 equal -c, which implies that c is equal to 9. First one's done. Next. Okay, and what I'm going to do here doesn't seem like it's fair because I can do it easily. You can't. I'm going to erase what I just did. I don't know. There. And there. And there. So I go back to this. And what would be another convenient choice for x? Yes, let x equal 0. Okay? And if x equals 0, what does the left-hand side give you? 6 is equal to, and x equals 0 here would be a, and the next one, 0, the next one, 0. So a is equal to 6. All right. All right. This is moving nicely, isn't it? Except getting that b. We got A, we got C. There's not any easy way to get the B. Okay? So here's what we do. Now this is a little messy, but it's not really all that bad. Okay? We write out what we have here. And that's 5x squared plus 20x plus 6 is equal to, and over here we had a times x plus 1 squared. Well, we know what a is, right? Right? It's 6. So it's 6, and let's square x plus 1. I mean, what's that? We know from right down here what it is. Right? What is it?
Is it square x plus 1?
Yeah.
X squared plus
That's it. X squared plus 2x plus 1 plus b. But we know what b is. No, we don't know. We don't know what b is, so let's write down b is b times. And here we just had x times x plus 1, because one of the x plus 1s went out. Well, I can do that one in my head. X times x plus 1 is x squared plus x, right? So b times x squared plus x. Right? Yes.
Can we start just that part again? I was writing the rest of the
Okay. All right.
But I'll find B.
Okay. We got our A and our C, right?
Yes.
Well, we still haven't figured out what B is. Okay. Now, to get B, unfortunately, it's a little more work. So what we're going to do is write down this equation here. Well, it's basically this equation right here. Okay? That was it right there. I may have messed something up there. I did. I really did. But it didn't hurt us any. I don't think. Okay? Let me make sure it didn't. I don't think it did. We started out with x equals -1, so that didn't hurt us there. And then we had x equals 0, and that still gave us, yeah, it didn't hurt us. We dodged the bullet there. Okay, so basically it's this equation here we're doing. 5x, the left-hand side stays this, and then we know what A is, 6 times this thing, right? All right, here's that. I heard you were here. I saw you, your stuff was here. Good to see you here. Okay. So, this is x plus 1 squared, which we wrote out here. Then plus b, and that's what we're looking for, and I'll multiply these two together. X times x plus 1 is x squared plus x, right? And then the c, we know what that is, a minus 9x. Right there. Got it? Okay, so what we do now is distribute, combine like terms, that kind of stuff. And I'm rapidly running out of room, so I'm going to come up here and do it. 5x squared plus 20x plus 6 is equal to 6x squared. You tell me what's next. Plus 12x plus 6. Keep going.
Write down our paper.
Yeah, right. Okay. Just in case my ugly writing here throws you off, let me get rid of that. What's next? Yep. Bx squared plus
x squared plus
b. Okay, bx squared plus distribute.
Oh yeah, I said plus b.
Bx distribute. All right. Okay. Minus 9x. All right. Now, still got a little bit of simplifying to do. So it's going to be 5x squared plus 20x plus 6 is equal to 6x. Okay. I'm going to do a little something else to simplify. Okay, hopefully this won't be skipping too many steps. Okay, here we have an x squared term, there we have an x squared term. Okay, so that's 6 plus b times x squared, right? And then we have a 12x minus 9x would be 12x minus 9x would be, anybody? Help me. Yeah, it's pretty hard stuff. 3x plus bx, so that would be plus 3 plus b x, right? Okay, you see that? The 12x minus 9x is 3x plus bx. It would be 3 plus bx. And then that accounts for all three of those x terms, and then all you got is a plus 6 left. Well, guess what? This plus 6 and that plus 6, we can just get rid of them because they're not going to mess each other up. Okay. Now, what we have here is one x squared term here, 5, is equal to 6 plus b, right? 5 is equal to 6 plus b, because that's the coefficient for x squared. It's got to be on both sides. So we have 5 is equal to 6 plus b. So what does that make b equal to? Negative 1. Now let's check that. Okay? Here we have, whoa, maybe I don't want to check this. Yuck. If b was negative 1, the next one doesn't make any sense. You have a 20 here would be equal to 2. And that ain't right. I made some really dumb mistake somewhere, and I needs to find it. Oh, wait. Yeah. Oh, I see where my mistake is. This is, I look down here, c is equal to 9 plus 9, not minus 9. So this gave us a 21 plus b. Whew. All right, y'all let me get away with that. That's bad on you. 21 plus b x. Okay, and now when you plug in b is equal to minus 1, what do you get? 20x equal 20x. Yes, that's right. That was a plus 9, not a minus 9. Duh. Okay. I was here, not here. Okay. So, we have our A, B, and C, don't we? Now we have to go back to that very first step that we've written all around and over and under everywhere else. So let me erase everything except the stuff we need. So I'm through with that's not actually in my way anywhere. But let me erase this, and that, and that, and that, and this. Oh, I erased too much there. Okay. That, and that. Oh, I don't need this anymore, or that anymore, or this anymore. That was what we had at the very beginning. So we don't need this. We're through with all this. That was all to get those coefficients, and we got them. Let's not erase them, though, because that's the other thing I need to keep. B is equal to negative 1. We need to hang on to that one. And C is equal to 9. We need to hang on to that one. And A is equal to 6. We need that one. Okay. So by judiciously saving only, or honing in on what we need, this integrand right here becomes that with these values in it. So our integral becomes the integral of A is 6 over x dx plus, no, minus, because the B is a negative, minus, and I'm going, yeah, okay, didn't think about it soon enough. that would be 1 over x plus 1 dx plus, I'm going to pull out the 9 because I don't think we need it there, 9 times the integral of dx over x plus 1 squared. Okay, and I could have and should have pulled the x out too. So let me do that too. Pull the x outside the integral because we don't really need it in there. And that would just be 1 over dx over. Okay. All right, I've got those plugged in, so now I don't need them anymore, right? Can I erase them? Yay or nay?
Yes.
Okay. Let me erase these then. I already plugged them in. So the purpose for this is to make integrals we can do. And can we do this integral? What's that?
Is that the log of
Log of x. So this is 6 times the natural log of x, and you really need to put absolute values because you can't take the natural log of a negative number, minus, what would that one be?
log of x plus 1?
Perfect. In absolute value, plus 1, plus 9. Uh-oh, what do we do with that one? Anybody?
Log of a
Nope. This only works for 1 over x. What technique might you use to help you with that? If a player's getting tired, you substitute them. Okay. Y'all were getting tired, weren't you? So let's do a substitution. Let u equal, isn't that how we usually start? And what would you let it equal? X plus 1. Then, what's the next step? du is equal to? dx, okay. So what does this integral be then?
Why do we have to use substitution?
You don't have to,
Okay.
but I thought it might make it a little clearer for you. What would it be? dx is du, right? And x plus 1 is u, so this is u squared. Now again, you might could have done this without substitution, but what I would do with a problem like that is rewrite that as 9 times the integral of, I don't like having my variable in the denominator if I can help it. So what would I write that as? If I move it upstairs, I have u to the negative 2 du, and I think we know how to do that, don't we? What? Okay. What would that be? Isn't that just a power rule problem?
U to the negative 3 over 3.
Wrong way. What do you do?
U to the, there's the U to the, it'd be negative U to the negative 1.
Yes, which would be minus 9 times 1 over u, right? U to the minus 1 is that. So here we have a 6 log absolute value x minus log absolute value x plus 1 minus 9 over u, basically. Oh, but what's u? What's u? All right.
X plus 1.
Yes, so let's rewrite that as minus 9 over x plus 1. And you don't need absolute value bars there. What else do we need? Indefinite. Plus C. Don't forget our little plus C. I think we have it. There is the integral of that thing. Now, there's a couple of different ways you could write it. This is perfectly fine, perfectly good. Or you could write this first one as log of x to the 6th power. Now, notice I don't need absolute value bars anymore, do I? Because anything raised to an even power is going to turn out positive. Okay? Minus log absolute value x plus 1 minus 9 over x plus 1 plus c. Or you can combine logs. That would be the log of x to the 6th over the absolute value of x plus 1 minus 9 over x plus 1 plus c. So all three of those are different ways to write this. None is any preferable to the other. That takes a little less typeset than the other two. So if you're worried about that, that would be your choice. But this is the first one you have. That's perfectly fine. Leave it like that. Or you can change. This is, yeah. Well, this one. Oh, this is part of that. Yeah. No? Yeah. This one went down like this. Okay. Or changing that. Let's see how they left. Oh, they left it. They put the absolute value bars over numerator and denominator. You don't need it because x6 is always positive. Log of x6 over x plus 1, absolute values of that, minus 9 over x plus 1 plus c. Done. So yeah, there was yet a fourth way to write this. The log of absolute value x to the 6th over x plus 1 minus 9 over x plus 1 plus c. All right, that's good. Any questions?
So why could we have not used the natural log of the plus 9 and then the integration of the dx?
Well, frankly, because that was a square down there.
Oh, okay.
Yeah. And you see the antiderivative of this is log of that. But that, you'd have, if you did the log of that thing squared, then you would have to then do chain rule times 2 times that thing. So you'd add a 2x plus 2, which you don't have there. Yeah, so no. That only works for something to the first power down there. All right, good question. Any other questions on that? All right, good deal. There is a technology blob at the end. You can certainly read that if you want, since I don't have Maple or Mathematica or TI Inspire. I'm not going to mess with that. So that done, let's move to quadratic factors. When using the method of partial fractions with linear factors, a convenient choice of x immediately yields a value for one of the coefficients. Okay. With quadratic factors, the system of linear equations usually has to be solved. A system of linear equations usually has to be solved regardless of the choice for x. Okay, that last one we had one more solution to do with the b, but we already had the a and the c. So that was pretty easy to do because we already had 2 out of the 3, so it was just, a little bit of work and not making any errors that you could come up with what the b was. However, with quadratic, you almost are never going to be able to get everything, so then you're going to have a system of linear equations, and they take a little more work. So we like work, so let's see what we can do with those. And without any further ado, they just give us an example. Okay, now this example 3, if you'll notice in your text, says, see larsoncalculus.com for an interactive version of this type of example. Now, I had a student in the morning class tell me that when she went to larsoncalculus.com or to actually calcchat.com, which is the homework exercises, that's what she was talking about. She said, I can usually find the problem, but they aren't numbered correctly. And immediately what that told me is they updated the edition of the book, but the calcchat.com may be based on the 10th edition rather than the 11th. So if you do run into that, beware, that could happen. Just look at other examples till you find the one you're looking for, unless you happen to be working on one that they stuck in an 11th edition they didn't have in the 10th. So then go to another one similar to it, and hopefully you can find that. All right, so let's do this. All right. Oh, my goodness. They were so kind to us. At least they started being kind. What did they do? They partially. They factored out an x squared plus 4. And what can you tell me about x squared plus 4? Can we factor it any further? No, because it's the sum of two perfect squares. We'll never, ever, ever, ever factor any further. So that's going to be our irreducible quadratic factor. You can't factor it any further. But how about that first factor? That's also a quadratic factor.
But it can be.
It can be, so let's factor it. What does that give us? X times
that would be x times x plus 1.
Minus 1, so no plus there, times x squared plus 4. That one can't be factored any further. So complete your factorization. They were kind enough to have started the factorization for us. Now, if they hadn't, we would have had a fourth degree polynomial with lots of other things in it, and we would have probably been pulling our teeth or hair or something. I have more teeth than hair. No, never mind. But it would have been much more difficult to see how to factor. They did the hard part of the factoring, left us the simple part to do. We've done it. So what do we do with that?
Let's say a over x.
Okay, yeah, we start with what the integrand is, 2x cubed minus 4x minus 8 over the factored form, which is x times x minus 1 times x squared plus 4. Okay, I like what you were starting, so you tell me, continue.
Yeah, I already written that down. So then you'd say
a over x plus b over x minus 1 plus
c over.
When you have an irreducible quadratic factor, it has to have a linear coefficient, not a constant coefficient, a linear coefficient. Always 1 degree less than the denominator. Now, when you add x plus 1 squared, it just kept having a constant. But this is a cx plus d, a linear numerator over x squared plus 4. Okay. Now what?
Can you explain that for you?
Okay. Earlier, you flipped back to your rules, didn't you? So flip back to your rules again. and see on page 551, if you got a text, bottom of the page there, the decomposition of n of x over d of x into partial fractions. That number 4 there, quadratic factors, those are going to be b1 x plus c1 for every degree that you factor you have. We only have one, so we just stop at the first one. And ours happen to be in letters of the alphabet cx plus d. You could have gone, if you had done the first one to be an a and the next to b1, then this would have been a bx to b2x plus c2 or whatever you wanted to call it. I just find it easier to just keep going on letters of the alphabet rather than messing with subscripts, which might mess me up later. Okay, now what do we do? What don't we like about that?
Oh, yeah, the common denominator.
Oh, we need to get rid of denominators, don't we? And how do we do that?
Multiply by common denominator.
Yes, and we already have it. It's that whole factored form down there. So we multiply this first one by x times x minus 1 times x squared plus 4. Multiply the second by x times x minus 1 times x squared plus 4. Multiply the third one times x minus 1 times x squared plus 4. And multiply the fourth one, I'll put that in parentheses, times x minus 1 times x squared plus 4. I ran out of room, but you got my general gist there, right? Now, the good news is the left-hand side, what goes away? Your entire denominator and the thing you just multiply it by, because you multiply by that denominator, all goes away. You're left with 2x cubed minus 4x minus 8. You know, I never would have started with this. I'm sorry I didn't do this earlier. There's a common factor of 2 there. So let's take that 2 on the outside and just leave this as x squared minus 2x minus 4. So let's get rid of that, okay? Why keep anything messier than it has to be? Okay. Now, on the right-hand side, in the first term, the x's go out, and you're left with a times x minus 1 times x squared plus 4. Continue. B. Okay, the x stays, but the x minus 1 leaves. Bx times x squared plus 4 plus, here I would put them in parentheses, cx plus d. Got to hang on to that. And what goes away? Okay, so this will be times, now these I think I will multiply to, well, let's not yet, x times x minus 1. Okay, that's our basic equation we're going to have to solve. Okay, and since I pulled the 2 outside the integral, now remember I've got to write that 2 in front of the integral when I go back to do it. Don't let me forget to do that. Okay, all right, what do we have here? What would you choose first? Okay, let x equal 1. Okay? Okay, what does the left-hand side become? It's negative 5 is equal to, and when you let this equal 1, guess what? That goes to 0. Yay! When you let that equal 1, that one goes to 0. Yay again! Okay, and those are factors, so the whole thing goes. So you're left with just B.
Multiply your 2 there to negative 5.
What's that?
Would you before we multiply your 2 to the negative 5 there? Because don't you have a 2 in parentheses up there?
Okay. This right here? This? Is that what you're saying?
No, sir. I'm talking about the negative 5 there.
Yeah.
Shouldn't that be multiplied by 2? Because of the...
Okay, yeah, we're going to pull the 2 outside the whole interval. We'll put it back in later. We're just going to deal with x cubed minus 2x.
All right.
Did I do that right? Yeah. Yeah. We're going to just wait and do the 2 by everything else there. So that's just b is equal to negative 5. Okay? Wait a minute. Maybe what you were saying. X equal 1. Is that what you're saying?
No, sir. I was talking about the 2 that we factor out of the...
No, not that. I had stopped here. I hadn't gone far enough. I just got this written. No, that we're going to leave factored out and put it in front of our whole interval. So this is negative 5. Here the a went to 0, and this whole term went to 0. And that's where, when you start asking about c, I thought you were saying this c. But this whole thing is 0, because that factor is 0. And this would be b times the x equal 1. What would this be? X equal 1. Yeah, that would be 5b. Negative 5 equal 5b. You see that? Okay. And that implies what? B is equal to? It's pretty easy. Negative 1, right? Negative 1, right? All right. Any other simple ones you want me to try? I'm going to erase my little arrows. I can do it easily. You can't.
2.
Second?
2?
No. Well, I mean, 2 might work, but it's not that easy. That you're still hard. Give me, huh? Easy.
0.
0, yes. When x equals 0, what does the left-hand side become? Again, it's pretty easy. Huh?
Negative 4.
Negative 4 is equal to, now you don't lose anything here, so you have to plug in x equals 0. Well, 0 minus 1 is minus 1. So it's a times minus 1 times, but 0 squared is 0 plus 4 is 4. So minus 1 times 4 is minus 4a. Right? By that? Okay. The b we already know, well, when you let x equal 0, that goes to 0. So that term all disappears. And when you have x equals 0, this one goes to 0. So that term disappears. So guess what we got a to be? 1. Excellent. Liking this okay. Until we get this far. And now things aren't quite so pretty anymore. We can't come up with anything else to set equal, x equal to that's going to eliminate a bunch of stuff for us. So that means we're going to have to deal with it. All right. So here's what we got left. The top equation is still the top equation. X cubed minus 2x minus 4 is equal to, but we know what a is. It's 1. So let's multiply this thing out. And you can do that by foiling, right? What would that be? X times x squared. X cubed. That's the first. The outer is, well, I'm going to do the inner next. Minus x squared. Then I'll do the outer. Plus 4x. And then I'll do the last minus 4. I just don't spell well sometimes, So that's the first one. Then the b is a negative 1 to begin with, so this is going to be minus, and x times x squared is x cubed, so that's minus x cubed. And then we got a,
Plus 4x.
yeah, but then times the minus 1, b is minus 1, minus 4x, right? Because b is minus 1. Okay, here's where we get into problems. Okay, plus. Okay, now I'm going to, okay, here's what I'm going to do. I'm going to write this as x squared minus x. Is that okay? Now I'm going to FOIL that one. What would that be? First is cx cubed. Then I'm going to do my innards plus dx squared, right? Now my outer minus cx, and finally my last. Whoa! No, 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 no. You almost let me get by with it. Let's back off a moment here. I messed up. Oh, don't erase that. Okay, I erased too much. Sorry. All right. Again, the first is cx squared. That's cx cubed plus cx cubed. Then we do our outers and our innards. Our outers here are minus cx squared, and our inner is plus dx squared. So this will be a d minus c x squared, right? Or you could write them out separately if you want to. That might be helpful. Yeah, let's do that. If that's okay. I think it'll work out better. That is plus dx squared minus cx squared. Okay, outers and innards. And then you wind up with a plus dx, right? That accounts for everything. All your terms, right?
Minus dx.
Okay. Oh, goodness, I'm old and slow. Yes, it's a minus dx. I'm sorry. I thought you were saying the x squared term. You're absolutely right. It's a minus dx. I don't know if I said it, but I wrote it wrong. Okay, minus dx. Okay. Now let's start combining like terms. Let's start with the cubic terms. Whoops, I was starting to really wipe them out. Here's an x cubed minus x cubed. I can get rid of those. Okay? I think those are the only ones that'll go that easily. Nope. Here's a minus 4x and a plus 4x. Plus 4x and a minus 4x. They went pretty easily. Okay? And we can look at both sides and see we got a minus 4 here and a minus 4 there. So they're going to disappear too. Right? All right. Now, so that leaves us in x cubed terms. Here we have a 1x cubed is equal to cx cubed. So guess what c has to be? Do you see that? On the left-hand side, you have 1x cubed. On the right-hand side, the only x cubed you have is cx cubed. That means c equal 1. Right? Yay or nay? Okay. So we got our c. We got our a, got our b, we got our c. Now let's go to the x squared terms. Okay? I don't have any x squared terms here. So this gives me a 0 on this side is equal to, and what we have on this side is d minus c minus 1. Because you have this one, that one, and that one. That's equal to 0. But we already know what c is, don't we? C is equal to 1. So we have 0 is equal to d minus 1 minus 1. So that's equal to d minus 2. So guess what d is equal to? 0 is equal to d minus 2. D is equal to, help me, Help me. 0 is equal to d minus 2. What must d be? dB. Second? 2. Exactly. Okay. Now we're going to check it. Okay? The x term says minus 2 is equal to minus d. Ha! What would d have to be? 2. If minus 2 is equal to d minus d, d would have to be 2, right? So yeah, it checks. We accounted for everything. We got it all covered. Okay. All that got us were our coefficients. So now we go back. Here's where I do a lot of erasing. Y'all can keep writing on the page. I have to erase because I don't have enough room. Okay. So I'm going to erase my factorization. That's fine. And I think I'll erase the denominator. Oh, that's not what I wanted to erase. Yuck. Sorry. This was over x times x minus 1 times x squared plus 4. Okay. Here's what I wanted to erase. I wanted that left in there. I wanted to erase this up here, this up here, this here, this here, that. I'll leave that, that, this, and that. Okay? And then I'll erase all the rest of this down to a certain point. B is equal to negative 1. I want to hang on to that. A is equal to positive 1. I want to hang on to that. All this can go. That was all scratch work to get the answer I wanted. C is equal to 1. I'll hang on to that. And D is equal to 2. I'll hang on to that. All that to get those 4 little numbers. Okay. So, now we write down our integral. 2, don't forget that, we factored it out, times the integral of,
1 over x.
yes, A is 1 over x dx. B was minus 1, so minus, and by the way, the 2's in front of all this. The integral of 1 over x minus 1 dx plus integral of x plus 2 over squared plus 4 dx. There's my integration. All right. Now I think I can lose these coefficients. If I wrote them right, I should be okay. And I sure hope. I had y'all checking me, and you would not let me get away with anything, right? Would you? All right. Now I can do the first 2 integrals without too much effort, I think. The third one, though. Actually, I'm going to do something that might look a little strange. I'm going to multiply the 2 inside everything. Oops. So I'm going to do 2 there. And I'm going to do a 2 here. And I'll do a 2 here. And there is a little bit of method to my madness here. Okay? What would this first one be?
2 times the log of x.
Absolute value x, right. Minus
2 times log of the absolute value of x minus 1.
Perfect. Now, I'm going to pause here for a moment. I'm going to multiply that 2 across the integral sign and make that a 2x plus 4. Now, it might look like the plus 4s is what I'm getting at. It's not. What I'm getting at is that 2x. Because I'll write this down this way at first. The integral of 2x over x squared plus 4 plus the integral of dx plus the integral of 4 over x squared plus 4 dx. Okay. Now, isn't that sort of correct? If I multiply this through, I can split this into 2x over this plus 4 over that. Right? Everybody agree or not? Is that too many shell games? Okay? Now, why did I want to do that, especially to this?
So you can substitute?
Yes, 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 yes. What would be our substitution?
Would u equal x squared plus 4?
Absolutely. Then, du is equal to 2x dx. Right? Ha! 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 That interval becomes du, which is 2x dx, over u. Right? I think we can do that one, can't we? Oh, but how about that next one? Oh my goodness, what have we done? Anyone have any ideas?
Well, what's that factor?
Yep. If it was a minus, it would. Not. It's a minus. It's a plus. X squared plus 4. When have we seen something like that before? Not a regular substitution, but a... This time we let the x equal something. And what might that equal? We usually do them when there were square roots there. This one doesn't have a square root, but I think it'll still work out for us. X equal 2 tangent theta. You want to try that? What's our next line? Then dx equal what? What's the derivative of tangent theta? Anybody?
Secant squared?
Yes, 2 secant squared theta. Now this may not work, but it has hope, doesn't it? D theta, don't forget your D theta there. Okay? What else might we need to do? Then also x squared. Let's go on and do the plus 4 at the same time. If x is 2 tangent theta, x squared is square 2 and you get 4. Square tangent you get tangent squared theta. That's the x squared part plus 4, which is equal to 4 times tangent squared theta plus 1, factoring out the 4. And what would that be? What is tangent squared plus 1?
Tangent squared plus 1 is, it's
squared. Pythagorean, secant squared theta. Okay. Now that we got those pieces, let's do that last integral. Okay. Last integral would be the integral of 4 times 4, or dx is 2 secant squared theta d theta, right? From there, over, and what's x squared plus 4? 4 secant squared theta, right? Oh my goodness, look at this. The 4's go out, the secant squared thetas go out. They've been dating, by the way. And you just have the integral of 2d theta. Right? All right, so let's go back and write our answers. 2 times the log of absolute value x minus 2 times the log of absolute value x minus 1 plus, now let's do this one. What's the antiderivative of du over u? Please say you remember.
That derivative of du over u.
Yeah.
Is
so we just did it up here.
The log of u.
U, and what's u?
X squared plus 4.
Yes, plus. And this didn't have a 2 in it, just log of absolute value x squared plus 4, right? But guess what? X squared can't be negative, can it? And you add 4 to it, and that surely can't be negative, so we can put parentheses around that one, right? Not that it matters. But log of x squared plus 4, because that was what your u was. And then this last one was, what's the antiderivative of 2d theta? This came out integral of 2d theta. Antiderivative of that? 2 theta, you got it. Plus 2 theta. Oh, but we don't want the theta in there. We want an x in there. Well, this is the place to draw our little triangle. Remember? We like drawing triangles. Let's take this one right here and change that around to be tangent theta is equal to x over 2, right? Well, I'll draw me a little triangle because I like drawing little triangles. Let that be a theta and this be a right angle here. And what is tangent? Taking oats away? Okay. Taking oats away? You don't remember that one, huh? Some old hen called another hen. Sine is opposite over hypotenuse. Cosine is adjacent. No, adjacent over hypotenuse. And tangent is taking oats away. O is opposite and A is adjacent. So opposite would be x, adjacent would be 2. Okay? Right? Now, with that right there, well, actually we didn't even have to do this. All we have to do here is say theta is equal to inverse tangent. I'm sorry, we didn't even need a triangle. Sorry, but I like the triangle, so I wanted to do it. But it's not necessary in this case. Right here we say theta is equal to inverse tangent of x over 2. So instead of theta, we say inverse tangent to, ooh, erase the wrong thing. Whoa, get out of there. Okay, go back and erase the right thing. Okay. from right here, 2 plus 2 times inverse tangent of x over 2. Get out of there, okay? And we got a plus c. All right. Now, I've already brought my 2's in and used those, so I think this is my answer. 2 log absolute value x. Are we running close to out of time? Oh, that's right. You had to leave early. Okay. So 2 times absolute value, log absolute value x minus 2 times log absolute value x minus 1 plus log of x squared plus 4 plus 2 times the inverse tangent of x over 2 plus c. That is a perfectly legitimate answer. Or we could have done this. We could have brought our 2 here and made it exponent, brought this 2 and made it an exponent, and then we would have added our things together, and that's be the log of, I'm going to put it all under absolute value sign. Well, x squared can't be negative. None of those can be negative, so we don't need absolute value signs, do we? Because the squaring of that will wipe out the need for absolute value bars, right? So this will be x squared. Let me see if I'm saying this yet. X squared times x squared plus 4 over x minus 1 squared plus 2 times the inverse tangent of x over 2 plus c. So that's about as simple as I can think to write this. Let's see what, oh, yeah. Yeah, let's see what they did. Which one was that? Oh, well, we're going to do it. Let's just see what they got. They left it in the other form. 2 log absolute value x, they didn't square, minus 2 log x minus 1, they didn't square yet, plus log x squared plus 4, they left that alone, plus 2 inverse tangent, exactly like I did x over 2 plus c. So they didn't get it into a simplified form. All right, let me erase all this because this is one that actually worked, okay? And what they did, though, they didn't factor out the 2. So they're going to come up with some different seeming answers, but we're going to wind up in the same place, okay? So here's what they did. They took that original thing, just the argument of the integral, the integrand, and wrote that as a over x. They factored the first, okay? And here's what they said they did that. A over x plus b over x minus 1 plus c x plus d over x squared plus 4. Always the irreducible quadrant factors you write with a linear coefficient, numerator. The others that are linear or powers of linear, then you write with just constant numerators, okay? And then you multiply by the least common denominator, which is that whole big denominator on this side, and that leaves you with 2, the numerator, 2x cubed minus 4x minus 8. We factored out 2 and came back for it. A times, because the x is canceled out, x minus 1 times x squared plus 4, plus bx times x squared plus 4, plus c, x plus d times x minus 1. And then we chose some convenient x's, like x equal 1, or x equals 0 they did first, gave us a is equal to 2. We got a is equal to 1, but remember we factored out a 2, so it still is, that works well. And to solve for b, you let x equal 1, which is what we did also, and you got b is equal to minus 2. We got minus 1, but as long as we factored out the 2. So that's going to work out fine. At this point, c and d are yet to be determined. You can find these remaining constants by choosing 2 other values for x and solving the resulting system of linear equations. Yeah, you could do that. They did x equal minus 1, which is okay. This is another way to do it. We didn't do it this way. And that gave a minus 6 on this side and then gave some values on that side. And when you multiplied those together, you got 2 is equal to minus c plus d. Well, then choose another x equal 2. That will work too. And you get 8 is equal to 2c plus d. Well, you could subtract this equation from this equation, and that would wipe out your d's, and that would give you 3c is equal to 10. How in the, no, is equal to 6, and c is equal to 3. Okay? And then, whoa, no, 3c is equal to 6, c is equal to 2. Yeah, and we had it 1, if you remember. And then d is equal to 4, which we had a 2. And it works out just as well as if you had factored out all those 2's to begin with, and then you would have factored them here as well. Okay, so this gives you 2 times the log of absolute value x minus 2 times the log of absolute value x minus 1, plus log of, and see, they split up that last one. They sort of cheated on it, but that's what they did. They split up the c into d. And this gave us log of x squared plus 4, and the last one gave us the 2 times the arctangent of x over 2, which is what I got, but they didn't show their work at all, plus c. And that's the answer they left it. Oh, wow. All right, any questions? Okay? Any questions on any of that? Okay. All right. So, they say you can use a graphing utility to find that out, and oh, wait, no, I'm sorry. That was example 4. I was going to do, we did example 3, we haven't done example 4. We need to do that, so we need to go back and do example 4. All right, we'll do it here. Do we have time? How much time we got? Do you have it? My watch is a little fast. Okay, let's see if we can do it fairly quickly, or at least get going on it, and maybe you can finish it at home. Okay, here's what we got. The integral, huh?
I'm just going to say it was dead,
I can't hear you.
never mind.
Okay. The integral of 8x cubed plus 13x over x squared plus 2 squared dx. Now the first thing always to check for is make sure this is a proper integrand, okay, a proper rational fraction, yeah.
That must be a
13,
13.
yes. Huh?
Just making sure.
Okay, yeah, plus 13x, okay. Now, is make sure that the numerator degree is less than that of the denominator. Well, that's a cube. This looks like it's a square, but you're squaring that. So if you squared that, you get an x to the 4th, which of course is more than, higher degree than x cubed. So yeah, we're fine now. All right. Now, at this point, you notice x squared plus 2 is an irreducible quadratic. There's nothing you can do with it. Nada, nothing. So basically, we start out with this. 8x squared plus 13x over x squared plus 2 squared. Now, our first step is to write, because this is irreducible quadratic, we write a c. We don't need to do c. We can start with a. Ax plus b over x squared plus 2. Remember, we start with the first power, and then we do another one, cx plus d over x squared plus 2 squared. That's our first step. Whenever you have a multiple, either of a linear term or a quadratic term, then you do first over the first power, second over the second power, but you keep your numerators in the same form. If this was linear, it'd be an A, and then it'd be a B, and then it'd be a C, as many powers as you have. Since it's a quadratic irreducible that's repeated, then they're all AX plus B, CX plus D. And since you only have two powers, you only have two terms. All right, so that's how you initiate, okay? Ooh, we don't have much time. I don't think we're going to finish this. So let's just stop now. We'll start over with example 4 next time. Remember that, so you'll be able to answer that question. We almost finished 8.5. Homework exercises here are any of the odds 3 through 19. They're all at Calc Chat. Number 7's at Calc View. Do either 21 or 23. They're both at Calc Chat. 21's at Calc View. Do any of the odds 25 to 31. They're all at Calc Chat. Either 33 or 35. They're both at Calc Chat. Well, let's see. Yeah, give those a shot. All right. And we'll pick up the rest of those later. Okay. Sorry, we didn't have time to finish this one, but I think it would have been way longer than what we had time to do. So, let's see, did I cheat you out of any of your